would like to thank the organizers again for the great job they did in organization of the school, and thank you all for having resisted to the end. So this is the final part when I'm going to talk about Lazarus Makai bundles and their role in the generic green conjecture. So let me recall the theorem of Lazarus. So if S is a very general K3 surface, C in S is a smooth curve such that the Picard group of S is generated by C, then C satisfies Green's conjecture. And why do so the first question, why curves on K3 surfaces? Why this preference for curves on K3 surfaces and not on other surfaces? So there are several reasons.
Excuse me, you're not saying any K3 surface where effect is generated by C. You're saying still it has to be general.
Well, it's the same. It's just that C has to be the generator of the Picard group.
If require peak and another generality condition, or just peak?
No, this is yeah.
So you could cross that very general.
Yes. It's superfluous. Yeah, you're right. Thank you. So why curves on K3 surfaces? So there, the first reason comes from, since we are interested in causal cohomology. So as I mentioned, we have restriction theorems so if L is
sorry, I forgot again. Such a curve C has maximal Clifford.
Yes, yeah, I will recall that in a moment. It's a part of the story, and it's an important part of the story. So the first reason is that if L is very ample on a K3 S, then for any C in the linear system, even any smooth, but it also works for irreducible, so it's for connected KPQ. The restriction maps are isomorphisms. So this holds for any P and Q and any smooth curve in the linear system. This means that not only by restriction we get canonical curves, which was obvious, but also causal cohomology is preserved, is constant, and everything comes from the surface. So that would be a good reason. And let me just remark that if Green's conjecture was true, so let's be optimistic and believe in the validity of Green's conjecture. That would also mean that for any curve on a K3 surface, so let me recall you that Green's conjecture is a statement about the Clifford index. We could read off the Clifford index from causal cohomology, but causal cohomology is constant, so that would also imply that the Clifford index is constant. So that would imply that Cliff is constant in the linear system. This statement, which was stated as a conjecture by Harris and Morrison, well, it was slightly different. It was with gonality, but it's true with Clifford index. So this is true. This is a theorem proved by Green and Lazarus. So this is consistent with constancy of the Clifford index in a linear system on a K2 surface is consistent with Green's conjecture. So that provides another evidence. That would provide another evidence for Green's conjecture. Now the second is that if peak of S is generated by OS of C, then the curves C is Brill-Noether-Petry generic. That was proved by Lazarus. Meaning that all the Brill-Noether loci are have dimension expected one, and they are smooth away of the locus where we expect to be.
And Brill-Noether?
Brill-Noether-Petry. This means that essentially it means that all the Petry maps are injective. Yeah, Petry. He used to be a high school teacher in a small German town, in Landau, if I'm not wrong. And he wrote very few papers, but all of them with very high impact. So in particular, Clifford index is maximal. And we could write down exactly the prediction of Green's conjecture in this case. And finally, another answer is that there's a lot of geometry involved. So this setup would provide us with a lot of geometric objects which we can actually use. Okay, and now about Lazarus-Feld Makai bundles, let me give you a little bit of history. So this notion began with two papers from the 70s, one of Sandona 74 and one of Miles 76. So what Sandona proved was the following. So if C is a curve on a K3 which is hyperelliptic or trigonal, then any other smooth curve in the linear system is hyperelliptic respectively trigonal. And Miles generalized this to a larger class of curves. So if C in S, again, a smooth curve on a K3 surface, and A is a base point free G1D on A and complete. And we suppose that D squared over 4 plus D plus 2 lower than the genus. Then this A is induced by an elliptic pencil on S. So in other words, if we have G1Ds with small d,
You mean a pencil of elliptic curves?
yeah, a pencil of, yeah, that's true, a pencil of elliptic curves, So this means that special geometry, very special geometry of curves on K3 surfaces have the reason, or a curve on a K3 surface will have a very special geometry because of the geometry of the surface. So that comes from the surface. The reason should be in the geometry of the surface. And this result, or these two results, were the motivation for the Harris-Morrison conjecture and the constancy of the gonality, which turned out to be false, but not that false. Anyway, it's true for the Clifford index. And the explanation is in the existence of these Lazarus-Makai bundles in general. So Lazarus-Makai bundle is an object which exists or on any surface, K3 surface. So let's. What is the idea behind this notion? So suppose we have a K3 surface S, and suppose we have a curve, a smooth curve. So C is in S. This is a K3 surface. And let's assume we have a, like in Miles' theorem, a complete base point free pencil on C. So this will give us a bunch of points. Then these points move in the linear system, right? So we have the points which pencil, let's say a G1D, which move. And now we would like to look at the surface itself. So let's forget about the curve for the moment. Let's just erase the curve. Pretend it hasn't existed. And let's have a look at these points. So we are still with some with a bunch of points which move, but on the surface this time. So now the question is why do they move? What does it mean? Points on a surface that move. So if we look at Miles' theorem, which is quite instructive, they move because they are all on elliptic curves on the surface, and these elliptic curves move. But this doesn't happen in general. So in general, we don't have those elliptic curves. So the question is why they still keep moving even if we don't have elliptic curves at all. And the reason is that there is a vector bundle, a rank 2 vector bundle involved. So the points move. The reason why the points move is that there is a vector bundle. And this makes sense because, well, points on a curve are zeros of sections in line bundles. But points on a surface, what they could be? Well, zeros of sections in rank 2 bundles, if we are lucky. Okay, so let's define these bundles. So A is base point free and complete. So if we just evaluate the sections, we get this exact sequence. And now the idea is, instead of evaluating the sections over C, we want to evaluate the sections over S. So we can do the same thing, just replacing OC by OS. We still have a surjective map. This time, this is a line bundle supported on the curve. This is a trivial.
How do you extend? Okay, you're now taking the surjection of OS to OC. Okay?
Yes, yeah, it's just a composition of this map. And the kernel this time will be, this is trivial rank 2 bundle on S. The kernel will be a rank 2 bundle on S. So FCA is a rank 2 bundle. So if we dualize this sequence, then we get K minus A, the dual, which I call ECA, and this is called the Lazarus-Makai bundle. Bundle associated to the pair C and A. And why didn't...
I mean, x1 of A, O is K minus A.
Yes, yeah, yes. So remark in...
That's KC. So here you're using the KB.
Yes, it's essential to have a K tree. So in Miles' case, ECA is just so if this is O of E, it's split. So it's OS of E, OS of C minus E. That explains why to prove this theorem, he doesn't really need to use the Lazarus-Makai bundle. It's the same. He just needs to look at these two factors to prove that they exist.
C minus A.
C minus A, yes, because the determinant. I'm going to write down all the invariants of ECA. The determinant, we see that since it's an elementary modification, it's C. It's O of C. So we see that these Lazarus-Makai bundles come with a God-given space of sections. So it's a space of global sections. Okay. Let me now find the invariants. Okay, what are the invariants? Are the following. So that of E is OS of C. The second chapter class, let's call this E, just to shorten the notation. So this is D, the degree of A. H0 is H0 of A plus H1 of A. So this is G minus D plus 3. H1, and this is important, of E is H2 is 0. So it has no higher cohomology. The chi of E tensor F, so F is FCA. This is twice 1 minus rho of G1D. And E is globally generated of the base locus of K minus A. So if the residual is also globally generated, then E is globally generated. So it has almost all the nice properties we can ask from a vector bundle. And somehow the guiding principle in this part is that Brilnetter theory of curves on K3 surfaces is governed by Lazarus-Makai bundles. So if we control Lazarus-Makai bundles on K3 surfaces, then we control completely the Brilnetter theory of curves on those K3 surfaces. So let me give you some. Let's ask now an opposite question. So suppose we are given. So suppose we are given E, a rank 2 bundle on.
You don't really need that A. You could just take a two-dimensional linear subsystem of H naught of A with generators.
You don't have this.
Then you miss that.
You miss that, and it's important in the computations. You really.
I was saying in the beginning.
Of course, you can define. Actually, you can define on any surface, if you. But then you miss many of the properties.
H1 of E, H2 of E is 0.
Yes, yeah.
That's why you use.
Yeah, and this is really important in specific calculations. If not, for example, if you work on other surfaces, you always have to be careful to impose those conditions, otherwise it gets out of control. So if we are given an arbitrary rank 2 bundle on S, when is E Lazarus-Makai bundle? So the question is, the answer is, so this is, of course we have to impose all these conditions, and so we need all the properties, all the invariants in the proposition, plus we need the existence of a space of sections, two-dimensional, such that if we consider the evaluation map restricted to the space of sections, the degeneracy locus sorry, yeah, thank you, lambda. Degenerates, so the degeneracy locus is a smooth curve. So we need to replicate this sequence. So this is the answer. So in particular, in flat families of rank 2 bundles on S, being Lazarus-Makai is an open property. So if in some parameter space of rank 2 bundles we have one Lazarus Makai bundle, then this will propagate on a Zariski open subset. So LM property is open. Okay, what is the relation with with the Petri map? So just let me recall that the kernel of the Petri map, this is since we work with G1Ds. By the way, the whole theory works for GRDs. So that's why I said Brill-Nutter. So the definition I gave only for G1Ds, but can be given for GRDs. So the whole Brill-Nutter theory, not only.
My question.
H
naught of A doesn't need to be.
Of course, yeah. Yeah, but you don't need to take two sections. You need to take the whole section. The whole sections to get again the vanishing of H1 and H2, and then get higher rank bundle. Yes.
You assume you must have rho is less than 0.
No, a rho can be bigger than 0. So the kernel of the Petri map is H0 KC minus 2A by the base point free pencil trick, which also follows from the sequence written there on the top, twisting by K of minus A and taking global sections. And if we play with the defining sequences, we will get, by restriction, a map like that. And on the other hand, if we take global sections, we will see that H0 of E tensor F is isomorphic to H0 of F restricted to C tensor K S of minus A. So somehow from these two facts here, so this exact sequence and this isomorphism, we feel the need to analyze the number of sections in E tensor F. So to analyze whether or not E is simple. So the whole somehow the analysis of various cases will give the following. So first, a proposition. This is due to Lazarus field. So if E is simple, then the kernel of the Petri map is 0. That holds also in higher rank. So this is a general fact. So simpleness means implies injectivity of the Petri map, and the fear.
Why? Because you move the C and then do the splitting.
Yes. E is simple and C general. You need to assume it's general. Yeah. Yes. Otherwise, it might not be true. Anyway, an analysis of the situation will allow Lazarus field to prove the Giesecker-Petri conjecture. So if peak of S is generated by C, then I should have, sorry, that's again general. Let me write this way. So then, and C in L general, then C is Brill-Noether-Petri generic, meaning that all the mu 0A are injective. In particular, this implies all the good properties for the Brill-Noether loci. So there are no, if rho is negative, there are no A's, and so on. Okay, and let's see how what's the role. So this is a quite wide subject. These bundles have many applications. For example, so Makai is here because he used them in the classification of Fano manifolds of co-index 2. They have many applications. So the point is that whenever you need to test one statement about vector bundles on curves or surfaces, it's a good idea to start with these Lazarus Makai bundles, see what happens. So either you find counterexamples or you test your statements. So they are good in many problems. What is the role of Lazarus Makai bundles? In Agreeance conjecture. So in Voisin's theorem, there are two cases. So one of them is the odd genus case. The other one is the even genus case. The even genus case, it's slightly simpler, but the idea is the same. So as I want to keep things simpler, let me just deal with the even genus case. So we have G to K, and I will explain what are the differences. As a K3 surface, and the Picard group is generated by O of C, so C squared is 2G minus 2. Then by the theorem of Lazarsfeld, the Clifford index of C is a K minus 1, and we expect from green K1 of C, Kc is 0. Now, let me recall that Voisin found a new description of causal cohomology in terms of the Hilbert scheme. So first, passing to the surface, this amounts to proving that Kk1 of S and let's call L OS of C, this is 0. So we have to prove this statement. Now Kk1 of S and L was, let me see if I should keep the same notation. So we have K plus 1 times S. Inside here we had the incidence variety psi k plus 1 with two projections, pi k plus 1 and the second to S, and so this is finite, and kk1 and S and L is the co-kernel of the restriction map from H0 S k plus 1 times S in that L k plus 1 so this just means the pullback to the same over the incidence variety. So if we denote by PR1 and PR2 the projections, I'm sorry, the notation is becoming heavy. So these are the projections on the first and the second factor. This is just the restriction of PR1 upper star that L k plus 1 over psi k plus 1. So she wants to prove that this map is surjective. This is curvilinear. So we need curvilinear subschemes. We need to work with curvilinear subschemes.
Tangent dimension 1.
Sorry? Yeah, yes. Okay, so she wants to prove that this map is surjective. So this is obviously H0 S k plus 1 C that L k plus 1. So basically we have this bundle that L k plus 1 here, and we take a pullback map of sections to here, and we want to prove that this pullback is surjective. So this is the situation. And ideally one would prove this directly, but unfortunately, well, life is difficult, so one has to find something else. So the first idea is to make a base change. So try and make a base change and see if this works. So the general situation is like we have so the general situation is that we have this psi k plus 1 we have this map pi k plus 1 which is finite over S k plus 1 C, and we want to prove that. So we have the bundle here. We want to prove that the pullback of sections will give a surjective map. So we want to make a base change. So we make a base change. Here we have a Z. Here we have a I don't know why. So if the space of sections gets bigger, so if when we take pullback here on the upper row and we get some injective map, and the pullback here at this level is surjective, then this will ensure surjectivity of the other map. So let's put here some J, here some, I don't know, phi. So if J upper star is injective, on global sections so we pull back once this guy here, and we pull back the second time here, and phi upper star is surjective on global sections, then pi k upper star here is surjective on global sections, and that would close the deal. So that's somehow the idea, to make a suitable base change such that things work. And the first base change that comes in mind is the one provided by Lazarus and Makai bundles. So let me just record some facts.
You want to show that all sections of C come from downstairs, right?
Yes.
So you send them to Y.
Yeah, I send them to a bigger space and
Come from Z.
come from Z. Then the
Why should they come to them from S?
well, you should use. So this is a finite. So you can use a trace map. It's a trace map argument.
Should it be like in Galois or no?
No. It should not be Galois. It's just a.
Use the trace map.
We use the trace map. Yeah. If it's not finite, then it doesn't work. But for finite, it works. So how do we use?
But this is a finite base change from C to S.
No, not necessarily any base change. It works for any base change. We can write down the details after. So how do we use Lazarus and Makai bundles to get a natural base change of this Hilbert scheme? Well, Clifford is k minus 1. I should have added here that the gonality is k plus 1. So this would provide us with points, exactly the same number of points as we want to. So we should use this information, this coincidence in numbers. So in any case, the Lazarus and Makai bundle in this here has very nice properties. So Lazarus and Makai bundle. So if A is a G1 k plus 1 on C, call E ECA. Well, the first remark is that E doesn't depend on C and A. So the Lazarus and Makai bundle is unique. It's one single Lazarus and Makai bundle that works for any curve in the linear system and any G1 k plus 1. So the difference is made by the space of sections, by the two-dimensional space of.
It doesn't depend on.
It doesn't depend on which curve in the linear system you take or what.
So whatever curve and the G1 k plus 1 you take, you get the same bundle.
Why?
Well, because, for example, one reason is that rho is 0 and E is stable. So this is rigid. Okay, so this will give a finite map from the Grassmannian to the linear system. Over each curve we have those finitely many G1 k plus 1s. On the other hand, vector bundles on K3 surfaces can be also described by a Serre's method, by extensions. So we can also present this E as an extension So for any S a global section in E, get an extension zero O E L times like C goes to 0, where C is the 0 subscheme of S. And then we get a map from P projectivization of the space of sections in E to the Hilbert scheme. And this is an injective map. Right? We associate to any S this subscheme, which is curvilinear. Then the first attempt would be to just to consider this projective space as the base change. So
it's given by 2 sections.
Why is it curvilinear? Well, if it's not, yeah, that's true. It's locally complete intersection. This is true.
One of the 2 sections must be true.
Okay, you're right. So you just get a map from an open subset. So anyway, the first natural base change to make is to take these subschemes that come from zeros of sections in the Lazarus Makai bundle. So the first attempt is to take Z to be this P, but this doesn't work. So the first attempt is a failure. However, Claire had the idea.
Sorry, but you said that this is injective.
Yeah, it is injective. This one is injective.
Yeah, but you want to use the trace map, so it should be subjective.
No, the trace map we use on the down arrow.
Yeah, on the vertical arrow.
Look, I mean, you have a section of C and you want to show that it comes from S. Okay? You point back to Y and then it comes from Z.
Yeah, but this doesn't work anyway. So this.
It was a question I asked you before. How do you find the section on, let me call S for S curvilinear, blah, blah, blah.
Yes.
How do you find the section on the lower corner, right corner? You take a section on C, you pull it back, Y, and it comes from Z, and then you must show that you get the section on S.
Yeah, I don't know. I have to think about it. But yeah, it's. We will.
I would accept that your explanation of trace if Z was dominating to S.
It doesn't need to be dominating. It's just that you need.
How do you extend? I mean, it could be that Z is a subvariety of S. Could be a.
Well, it is a subvariety in general. It is a subvariety.
So why does the section extend from Z to S? Well, there must be more to it then.
Yeah. Well, I don't know. I have to think about it. So I don't have a.
Explaining everything.
Yeah. Anyway, this doesn't work. So this attempt doesn't work anyway. So then Clairvoyant had the idea to do a different base change, which is, so this P will parameterize zeros of sections in the Lazarus-Makai bundle. So it doesn't work because, well, this P is too small. And then she had the idea to replace one of these points in the support by a general point. So replace P by another space which would parameterize. Of course, you have to give a sense to this, to what's here, but it makes sense. So a parameter space for these objects, where x is in the support of V of S, and y is general. So just replacing one point, pretending that then one of the points in the support was a general point in the surface. And this space gets big enough to make things work. So this P prime does work. But this requires a lot of computations, just to show that this is the right choice, and be careful with the base change and analyze all these maps. And since we are all getting tired, I will just say a few words on how to deal with curves, or curves on arbitrary K3 surfaces. This is joint with Gabi Farkas. So again, thanks to these techniques of Lazarus-Makai bundles, we understand. So the exceptional curves are understood. So essentially, any exceptional curve, so they are all of type 2H plus gamma, where gamma is a rational, smooth rational curve. It's a line, actually, and H will compute the Clifford index of any curve in the linear system. So, except for this case, which we have to treat separately, the idea is to prove that. So the idea is to prove that if C in L is general and non-exceptional. Sorry, there are also plane curves on double. If we take a double cover of P2 ramified along a smooth sextic, then there are also plane sextics in among those cases. But these are, so except these ones and the plane sextics, these are all the exceptional cases. So if this is a general non-exceptional, then orthogonality D bigger than 3 at least, then C satisfies that condition on brillianter loci, which ensure that Green's conjecture is true. And in order to do that, we have to do it in family. So the advantage of working in a family of curves in a linear system is that these brillianter loci also can be put in a family. So we have some W1 G minus D plus 2 that go over the linear system. Actually, we can write this and put smooth here, the locus corresponding to smooth curves. So the fiber over any curve is just the corresponding W1, what is the degree, and then this loci W1 G minus D plus 2 correspond to parameter spaces of Lazarus-Makai bundles. And if those Lazarus-Makai bundles, so this might be quite, might have several irreducible components, but since we work with the general element in the linear system, we are only interested in those irreducible components that dominate the linear system. So we are interested in dominating components. And if the general Lazarus-Makai bundle, or the Lazarus-Makai bundles corresponding to a general pair here will be simple, then it's quite easy to see that we have the good dimension. So actually what we want to prove is to prove that the dimension of this locus is G minus 2D plus 2 plus the dimension of the linear system. So 2G minus 2D plus 2. So we want to bound the dimension of this loci, and if the bundles are simple, then it's easier. If it's not simple, then we have some spaces of extensions. So all the game is in computing the dimension of these parameter spaces. And we obtain the desired bound. So in conclusion, Green's conjecture holds for any smooth curve on any K-tree surface. Well, the exceptional cases are treated separately, but it's not much of a difference. So I think I will stop here. Thank you very much.